Hello and welcome to the equivalent resistance video tutorial. Here we have a circuit with 5 resistors, 5 ohms, 4 ohms, 10 ohms, and so on, and a 12 volt voltage source. What we are going to do is replace all of these resistors with just one resistor that has the same equivalent resistance as those 5 when they're put together. So to do that, first thing to notice is that this area right here is a node. What that means is that there are no circuit elements in this area, just wire. So the 6 ohm, 4 ohm, and 3 ohm resistors all basically lead to the same spot, which is right there. On the other side, we have a node here, where the current would come in through the 10 ohm resistor and out through the 6 ohm and 3 ohm resistors. The reason why this is important is because if you look carefully, the 6 ohm and 3 ohm resistors are actually in parallel. What that means is that the current comes in from this direction and splits. Some current will pass through the 6 ohm resistor, while some current will pass through the 3 ohm resistor. But no matter which resistor the current passes through, they both end up in the same endpoint, which is right here. So we can actually redraw this circuit to make this more clear by taking this wire, and instead of connecting it right here, what if we connected this wire right here? So in the more simplified circuit, nothing has really changed. We're just moving our contact point from way over here to right there to make the circuit more visually appealing and make more sense. So here the 6 ohm resistor is up here and the 3 ohm resistor is right there. We can solve for the equivalent resistance between the 6 ohm and 3 ohm resistor by using our parallel equation. So to figure out what resistor would replace these two, first off we're going to expect an answer less than 6 or 3, and that is what we get right here. The way we're going to do that is 1 over R equivalent is 1 over R1 plus 1 over R2, and if there were more in parallel, this could just be 1 over R3, 1 over R4, forever. And so we have a 6 and a 3 in parallel, and here they are right here, 6 and 3. So 1/3 is the same as 2/6, and so 1/6 plus 2/6 is 3/6. Now remember, this is not the equivalent resistance, this is 1 over the equivalent resistance, which means that you need to take the inverse of both sides of the equation. So R equivalent over 1 is equal to 6/3, and 6/3 is 2 ohms. So because it is easier for the current to travel through both directions than just the 3 ohm resistor. If this was just a 3 ohm resistor, let's say this is not here, it's going to be pretty difficult for the current to travel through, but by opening up another gate, it allows another route for the current to travel. We would expect the equivalent resistance to be less than our smallest resistor, and sure enough, it is. So we can take these out and we can redraw them with just a 2 ohm resistor right here, which is what we see here. So here we have the 2 ohm resistor that's replacing the 6 and the 3. Now we can see that the 10 ohm resistor and 2 ohm resistor are in series. What that means is that as the current travels down the wire and travels through the 10 ohm resistor, it has no choice but to also travel through the 2 ohm resistor. There's no other possible direction it could travel. So we don't really need to say this is a 10 and a 2. We can just combine those and say that it's a 12. And now this answer you're expecting to be more than your highest resistance. This is because it is, let's pretend this doesn't exist. The current's traveling down here and it has to go through a 10 ohm resistor. Well, that's difficult. It's more difficult to also have to pass through a 2 ohm resistor. So the equivalent resistance is higher than either of these. And it's simple enough, you just add them together to find out what that is. So we're going to take these out and replace them with just a single 12 ohm resistor, which is what we have here. Here we have a 12 ohm resistor taking the place of these, and now we have a new parallel circuit right here, because as the current travels down, some of the current will travel through the 4 ohm, some will travel through the 12 ohm, but both will end up at the same node down here. So we're just going to use the same equation from before. Again, we should expect an answer less than 4 and less than 12. 1 over R equivalent is 1 over R1, 1 over R2. So here they are, the 4 and the 12. 1/4 is the same as 3/12, which is 4/12 when added to the 1/12. This is not R equivalent, this is 1 over R equivalent. So take the reciprocal of this and the reciprocal of this. So R equivalent over 1 is equal to 12 over 4, which is 3, which is less than both 4 and 12. So we're going to take these resistors out and replace them with just a 3 ohm resistor, which is what we see here. So now our circuit is the 12 volt voltage supply and a 5 ohm and 3 ohm resistor. These resistors are in series, and there's no need to put a 5 ohm resistor and then have the current travel through a 3 ohm resistor. It's the same to just have an 8 ohm resistor and have the current travel through that resistor instead. So we can take these out and just have an 8 ohm resistor in their place. Now that our circuit has been significantly simplified, we can use Ohm's law to determine the current in the wire when leaving the battery. The voltage is equal to the current times the resistance. 12 volts is equal to current times 8 ohms. So current is 12 divided by 8, which gives you 1.5 amps. Take a minute to notice that this current is only applicable here in this junction, not in any of these earlier parts in the circuit. It's not here or anywhere else, because all of this part of the circuit has been changed to find an equivalent resistance. This current, however, will be 1.5 amps. Thank you, and this has been the equivalent resistance video tutorial.